Okay, so the recording has started. So I was saying, go to this URL, load the CSV. You'll see that it contains basically advertising data. You'll have two columns, one for television spending, one for spending on radio, and you'll have to predict what are the sales. So what you have to do is first part, read the data, then create a train test split. That is, don't train on everything. Use 80% of the data for training, and then we'll test it on 20% of the data. Okay. So once you're done with this, let me know, then we'll proceed. Raise your hand in the chat once you're done. Is anyone done? Okay, so I'm assuming you've loaded the data. So we have a data set. We'll just use pandas, import pandas as PD. We say, yeah. So our data looks like this. We have television spending, we have spending on radio, and we have spending on sales. What I want you to do is, in this data set, if we have if we have 200 rows, so use 80% of the rows for training and 20% will test on. You have studied, I believe, Least squares, yeah. You've studied least squares in class. So use stats model library where you have ordinary least squares. Try to fit the data, see what and report, then you can report the root RMSE. Yeah, that would be better. So report the RMSE score on the train and test split. Does anyone have any confusion in this? Take 15 minutes for doing that, then I'll show you how to do it. Any confusions? Is it clear? Can you raise your hands if it's clear? Okay, so it's 7:15. Take till 7:30. Afterwards, I'll show you what to do. So you have the data, use 80% for training, 20% for testing, and use stats model to train a linear regressor. So anyone, any progress? Is anyone halfway there, maybe stuck somewhere? Okay, good. Yeah, if you use sklearn's linear model, it's correct that way. But I mean, in class, you did it using starts model, so I'll prefer using that. In practice, I would also use sklearn, but since you've studied starts model, maybe use that. This is correct, yeah. So is anyone else done? You should at least try. Okay, so let's start. So we have the data. The first part is to create a train test split. So I asked you to use 75% of rows for training and the rest for testing. So a simple way to do it is our data frame has indices 0, 1, 2, 3, 4, and so on. We can take the first 75 for training and leave the rest for testing. So let's say we do split index is equal to, we have length of the DF multiplied by 0.75. Now this will be a float. So let's convert that to an integer. If we, for example, print this, we get 150. So the first 150 will be used for training, rest of it for testing. So if we split it, we'll get let's say x underscore train, x underscore test. We need two things. Similarly, we'll have y underscore train and y underscore test. So in x underscore train, we don't need the sales column. Okay, so what we will do is we'll say df dot drop the sales column, and you will find this sales in this axis, axis 1. By default, it searches in axis 0. We're asking it to do it in axis 1. So I'll ask it to drop the sales column. Once that is done, I want you to pick the first this many indices as I have supplied. Okay, so we have this. Next, we will do the same thing for the test set. We'll say df.drop sales x is equal to 1. Notice that when we do df.drop, we are not modifying the original data frame. It returns a new data frame, so the original is still intact. So this time we'll say .iloc, but begin at split index and take the rest of it. For Y train, we can simply work with sales. So we'll say sales, ILOC, split index, and then df dot sales ILOC, start at split index and end there. So if we have these, so let's say length of X train and length of X test. So this returns 150 and 50. So there's just one problem with that. Let's say we print X underscore, or maybe let's say Y underscore train dot max and Y underscore test dot max. We see a difference here. That is, for example, 19. And for example, if I plot the mean for the training set and the test set is quite different. So this is often a problem when you train on something and test on another thing. You want the two to be from the same distribution. This happens because the data set has been sorted so that the sales are in increasing order. 1.6, 3.2, 4.8, 5.3. Okay. So what can we do? The idea is before you split, you should always shuffle your data. So how do you shuffle your data?
Hello, am I audible?
Yes, sir. Hello. Yeah, can you hear me?
Yes.
Yeah. So up to what point were you hearing me?
I restarted actually. So I think you were explaining about the X mean and Y mean and
Uh, Okay, yeah. So let me repeat this part. So I was saying, if we if we take the train and test set before shuffle, I mean, without shuffling the data, it may so happen that we take the smaller values in the train set and leave the bigger values in the test set, and that may lead to a, I mean, the distributions are not the same. So if you fit it on the training set, it may not generalize to the test set. So you should always shuffle the data set before you split. So a hack for shuffling the data set is to use sample. Remember that in sampling, if you provide a fraction, let's say 50%, it will pick 50% of the rows at random without replacement. If I ask it to pick everything, the only thing is it will pick all of the rows, but in a random order. So for example, if I print it now, we see that the indices are not in order 18, 170, 100, 798. So it has been shuffled. So let's proceed after this. And another thing is we can reset the index. So afterwards, we saw that we can use stats model OLS. Yeah, so we have least squares. So for that, we have to import stats models.api as SM. Then we need to create a model. So we'll say our model is equal to sm.ols. Now this takes two things, an endogenous variable and an exogenous variable. Okay, so the exogenous variable, the endogenous variable is the basically the target and the exogenous is your data. So in endogenous, you will supply y underscore train, and in exogenous, you will supply x underscore train. So we are missing one point, that is, if you would remember, yeah, it's working. So a linear regression model, for example, in this case, when we have two columns, it will look something like this. For example, x0 or a plus b times x1 plus c times x2. Okay, something like this. So when you fit the OLS model, it wants to predict these three things, A, B, and C. But to predict A, it wants a constant attached to it. That is A times 1, something like this. Okay. Thing is, our data set doesn't have ones in it. So it is the job of the developer to append a column of one so that it can predict the constant. So to do that, stats model provides a function. It says sm dot add constant. So all it does is it prepends a row of ones to your data set. So if we try that, let's say we have x underscore train. Notice that it has appended a constant all ones. Okay, so this helps in predicting the intercept. So we have to do it for the train as well as the test set. So we'll say x underscore train is equal to this, x underscore test is equal to this. So we have done it for both of them. If we just pass the model to this and then call fit Let's say results is equal to model dot fit. We have our linear regressive. We can print the model parameters. Yeah, so we have the model parameters. We have constant is this much, TV is this much, and radio is this much. Does anyone have any confusion up to this point?
Sir, could you please repeat the concept of sm.ols? What's actually how we are using this?
This one, least squares. You're talking about OLS, right?
Yes, yes, yes. sm.ols.
Yeah.
How?
Yeah, OLS is just least squares actually, what you read in class. That is to, for example, you have linear regression, you can solve it either using maximum likelihood or you can just use least squares. So least squares tries to minimize the residuals. It will fit a line and it will compute the residuals. It will try to fit a line such that the residuals are reduced.
Oh,
If your data is in, yeah, in fact, if you have less data, OLS has a fixed formula. That is, you just have to do XX transpose inverse and so on. So you directly get to the solution. But in case you have a lot of data, they often use gradient descent or other optimization methods. But the core idea is to minimize the residuals. Should I go on?
yes, sir.
Yeah. So we have our parameters. So now what we want to do is we want to compute the RMSE, the root mean square error. We want to do that to check the performance of our model. So we'll do it for training set, we'll do it for the test set. So how do you do that? We'll say, let us say predictions, pet underscore train is equal to, you will use this part, what you got after fitting the results. You'll say results dot predict and just pass it x train. We have pred underscore train. If we have a look at that, we have these values. Okay. Similarly, we'll have pred underscore test is equal to results dot predict x underscore test. Now to compute the RMSE, we can create a function. Let's say we have defined cal RMSE. It takes two values x and y. Now what do we want to do in RMSE? You just iterate in the opposite direction. So first compute the error x minus y, square the error. Okay, so we have the error, we have the square, take the mean, and finally root. So np dot sqrt, and we want to return this. We can also specify that I want these to be numpy arrays. And to assure that they are one dimensional, we can say x dot travel, y is equal to y dot travel, and we have our function. NP is not defined. Yeah, so we have our values. Let's check one thing. Is spread train a numpy array or a pandas array? Yeah, so it's a pandas series because the training data was in the form of a series. To avoid that, we can actually do it here. That is, after we took LOC, we could use only the numpy values. We had values here, values here, values here, and values here. Yeah, so it looks like this. This time we have np.sqrt, and then we can just print RMSE train is equal to cal RMSE. We'll supply x and y. X will be bread train and y train. Similarly, we'll have RMSE test. That will be cal RMSE red test comma y test. So to reduce this thing, you can do 0.4f formatting. Yeah, so we have good performance. So our RMSE for training is 1.6, our RMSE for test is 1.69. Any confusion up to this point? Do you want me to go over anything again?
Yeah, can you show the code screen? Actually, I'm stuck on this pred underscore train. It's giving me an error.
Red underscore train, uh-huh. So
Uh,
did you use this part, predict?
Predict, yes, I did. It's giving error in this line itself. Pred underscore train. It's saying raise back cell line this train. It's saying value error.
Same value error. So by the way, did you use this part or this part when calling predict? For example, the module you define and what you get after fit, there's a difference. You have to use what you received after fit. So which one did you
I'm
use?
using that results. I'm doing it
Okay,
from
so you're using results and
mm,
you're passing it X train. So can you check the shape of X train?
shape of extreme. Okay. It will be x train dot shape, right?
Yeah, X underscore train dot shape. Yeah.
Saying 0, comma 4.
Yeah, so that's the issue. Your training set should be of this size, 150 by 3.
Okay. Okay, maybe I did something back there.
Yeah, in the pre-processing, something's wrong somewhere.
Hmm. I will check later. Okay.
Okay. Okay, no issues. Okay, so everything is clear up to this point. So let's move on. So let us say we want to.
Hello.
Yeah, hello.
Yes, just want to confirm. Suppose like if there is a the value of the RMS 10 and RMS test will depends on the our data. So if this
Uh-huh.
value is near about, then our model is good, means good, else it is not good. It means
So if I understand correctly, you're saying if the train RMSE and test RMSE are close, can we
yes,
conclude our model is good? Is that the
yes,
case?
yes.
Not necessarily. So let us say our data is underfitting. Underfitting means the training
Yes.
itself is poor.
Means it is more
So
bias.
yeah, it has more bias. So in that case, my train and test may be close, but both of them are bad. Okay,
Okay.
correct?
Yes.
But if I'm confident that my training RMSE is good, then if my test RMSE is close to the training RMSE, then I can conclude that I have my model generalizes well.
Okay. So is there any like value which may be like RMS range will be like in this range, then our model will be good.
I mean, it depends. I mean, how much you can tolerate. Because remember, RMSE also depends on on the scale of your data, right? So
Yes,
for
yes.
example, if you all of your data is in the range 0.1, you expect an RMSE to be small. But let's say you're dealing with data that's in thousands, then you expect the RMSE to be big as well, right? Unless you normalize.
Mm. Thank you.
Make sense?
No, now I'm good. Good. Now I got the answer.
Okay. Okay.
Thank you, sir.
Yeah. So Okay, no issues. So I was saying let's move on to visualization. So let us say I was only working with TV column. Then I had one column and one prediction. In that case, I could have plotted a line, correct? Where on the x-axis I would have TV, on the y-axis I would predict my sales, and then I can fit a line that is, am I doing good or not? But in this case, I have two variables. So my decision boundary would be a plane rather than a line. Does everyone agree?
Can you repeat?
Yeah, so I was saying, let's say our data set only had TV column and we were predicting sales. Okay. So in that case, our regression would essentially be a line mx plus c, right? Mx plus c would
Yes.
be line where, yeah, where x would be TV. So I can in fact write it. M times TV would give us sales, correct? So I can very easily plot it on a 2D plot where on the x-axis I will have TV, on the y-axis I will have sales, and I can even plot this line, which would be my regression line, correct?
Yes, sir.
Right.
Yeah, but this time I have two things. I have A times TV plus B times I have, I think, radio, and I
Radio.
have a constant. So notice that this thing will be a plane. It won't be a line. I have two variables, right? A TV line and a radio line. So to plot this, I have to make a 3D plot, correct?
Yes, sir.
Yeah, so let's try that. Visualize the regression plane. So for regression, for any plotting, we'll need import matplotlib.pyplot as plt. So if you would remember last time we used to do this np.linspace. If you're with me in the earlier sessions, we used to do np.linspace. What it does is, let's say I'll say 0 to 10, give me 50 values. It returns an array where you start from 0, you end up at 10, and between 0 and 10, it will give you 50 values equally spaced. So this gives me an x-axis, right? So for example, I'll say x range is this. Similarly, I'll have a range for my y values, which is np.linspace. For example, 0 to 10, and I'll have 50. So now I have two ranges. So I have x-axis and I have y-axis. But I have to create a volume. Think about it. This will generate a plane. That is, I have x values, I have y values. But to generate a plane, I'll need, for example, one value from x and all of the values from y. The second value from x, all of the values from y. Does it make sense? No? Makes sense?
Yes, sir.
Confusion?
Yeah, got it.
Yeah, so maybe let me show you a plot. So for example, can you see this?
Yes.
Yeah, so for example, in this case, let's say my TV value is 150. I have to have all of the values for radio against it. Similarly, for 200, the full range for radio, the full range for this. Okay, so I have to create what's called a grid. So to do that, you'll say mm, np dot mesh grid. You'll give it x range and you'll give it y range. So this essentially creates that volume for you. You'll say that my x-axis is this, my y-axis is this. Give me all possible pairs x, y, x, y, x, y, which gives you a mesh. So you'll say my capital X and capital Y, these are now matrices. So now you have essentially created a volume. Now within the volume, I want to plot my plane, my regression plane, and I have the equation for that. So remember that we have the parameters, these, right? Here, the first one is the intercept, and these two are for the TV and radio. So if we do intercept is equal to results dot params 0, and then we can say c0 comma c1 is equal to results dot params 1 comma results dot params 2. So now I have my intercept, I have c0 and c1. Now that I have all possible pairs for x and y, I can compute my plane like this. That is, I have c0 times x plus c1 times y plus my intercept. Any confusion here in this line? Clear?
Sir.
Yeah. So I have my plane. Now we have to plot the plane. To plot the plane, we'll create a figure. So let's keep it in this row. We have fig is equal to plt dot figure. Let us set the fig size to be 8 by 8. Now, because we have to do it 3D, there is one line that you should memorize. For example, fig dot add subplot 1 1 1. This essentially says one row, one column, first one, only one subplot. So you ask it for one subplot and you say, I want to project it to 3D. Now it can work with 3D. This is all you have to do for 3D plots. Once you've done that, you'll say ax dot plot my surface and I'll give you my values. There, I'll say I have x values, I have y values, I have z values. Okay, I have these three, and maybe we should change the x and y range to be, for example, we have dftb dot max. How much is that? Is it taking so? Yeah, so 296. Let's keep it to 300, and similarly for radio. Yeah, so we'll keep it as 50 or maybe 60. Let's have 100 values here and 100 values here. So if we try to plot this plt.show, let's see what we get. So do you see that? Is it visible?
Yes, sir.
Yes.
Yeah. So we have our plane. The only thing is we'd maybe like to see it from a different angle, because here it's not, I mean, easy to see which part is higher, which part is lower, and so on. To control the rotation, what you can do is ax dot view init. That is the initial view. You need to supply two things. Azim is the azimuthal angle. It says how much do I rotate about this axis. And another one is elevation. Elevation says at what angle should I look at the graph from. That is, let me show you. For example, if I set both of them to 0, we are at 0 degrees in this rotation and the elevation is 0. If I, let's say, take it to 30 degrees, I have rotated by 30 degrees, but I'm still looking at it from an elevation of 0. If I increase the elevation to, let's say, 10 degrees, now I'm looking it from a little up, further up. Makes sense?
Yes, sir.
Yeah. So we
So,
have the surface. Yeah, so we have the surface. Let's also plot the points so that we see how good is the fit. So what we will do is we'll say ax dot scatter, just like plt dot scatter. We'll say plot the axis as df dot tv. On the y-axis, I want df dot radio, and on the z-axis, use df dot sales. Okay, these are the true values, the ground truth values, not the predicted values. So these values I want to plot in black. So let's see. So is it visible?
Yes, it's visible.
Yeah. So let's look at it from a few different angles to maybe find a better visualization. Let's say 70-10. Yeah, this is maybe somewhat better. Okay, let's say, yeah, this is best. Yeah. So do you see we are looking at it from an angle that the plane looks like a line, and we see that it is actually a pretty good fit for our data. Correct?
Yes, sir.
Yeah. So the so the only issue with these kinds of plots is you need to do a lot of trial and error to find the correct view. Okay. That is, I mean, for example, we had the options from 0 to 360, and here as well, we had the options from 0 to 360. So it takes a lot of trial and error. So whenever you work with 3D plots, try to use this library, Plotly. Plotly allows you to create interactable these. For example, if you look at that, I can zoom in and I can also rotate my data. And if we can do that in our case as well, it would be a lot easier to visualize the decision plane as well as the individual points. It also tells me the individual values. And if I zoom out or zoom in, I can clearly see around me. Make sense?
Understood.
Yeah. So let's do that.
Hello.
Which- Yeah.
Sir, could you please go to the previous like code, like just scroll up little less. Yes.
Uh,
Sir, could you please explain the concept of triple one, like what's exactly?
yeah. Triple one essentially says the first number says how many rows, the second number says how many columns, the third one says which one of them. So let's say I had said 2, 3, 1. That would mean 2 rows, 3 columns. That would mean a total of 6 subplots, correct? And from the 6, use the first one. So 111 essentially means just one subplot.
Okay, sir.
Anything else?
No, sir.
Okay. So let's visualize it using Plotly. So Plotly requires um, import plotly dot graph objects as go. In this case, we already have the X range, Y range, X and Y. Okay. So what we want to do is we also have the Z values. We want to create a figure. Plotly has its own figure. So go dot, you can look this part up when you maybe learn it later. Plotly, it has a very good documentation and interactive, I mean, sessions. So what we want to do is we want to create a figure within which we supply our data. Our data in this case is a surface. Remember the same thing. So we'll say go dot surface. My z values are z values. My x values are x range. My y values are y range. Notice that in this case, I did not pass the mesh. I just passed the linspace, this thing. Plotly itself creates the grid. It doesn't need the grid in this case. So I'll say my z values are these, my x values and y values are as follows. And let us say we pass a color scale as burgundy. If we do fig.show, yeah, so it may look like we don't have, I mean, a plane, but if you just um, tilt it a bit, you see the plane like this, and we can rotate it to better visualize it. Okay. And you can obviously zoom in and zoom out, and you can also save this plot if you want. For example, download the plot as PNG in a particular orientation. Now we have the plane. Let us add the points as well. So in our figure, let us do add scatter 3D. This time I'll pass X value same as before. Okay. We did scatter here. X is DFTV, radio and sales. We'll pass X as TV. Y is radio. Z is sales. And when we plot these points, I don't want them to be connected. I want them to be individual markers. Okay. So we do this thing. And if we plot this, what's wrong? DF scatter 3D. Yeah, so the points are a little big. Let's take care of that. We'll say marker is equal to size. Size is, let us say 3, and yeah, the size is okay. And color, let's say black. So if we look at it now, for example, let us tilt it to this point. Yeah. So do you see we're actually doing pretty good? The plane from this angle looks like a line and we are perfectly fitting the data. Oh, it obviously has some noise, but in the linear models, we are doing pretty well. Any questions? Okay, so moving on. Yeah, so before we go ahead, for people who are maybe joining my sessions for the first time, you'll find all of the code at this repository. You don't have to take screenshots or anything. So data analytics with Python, week 8, I'll upload the code here. Okay, so let me share the link with you. So there are a few things that we could have improved. So for example, in this case, Ankur's method is actually better. If you are aware of scikit-learn library, it gives you a function, train test split, and that essentially does this for you. You don't have to pass anything. You say train test split. I want to split my data frame. From the data frame, I want to, basically say dot draw sales. This says this is the X data. Then I'll also pass the Y data and I'll say my test size is, for example, 0.15 in this case. This will generate X train, X test, Y test, all three of them. Okay. So this is a quick way to do that. Another thing is, rather than using stats model and taking all of these steps, you can also use scikit-learn's linear regressor. So for example, from sklearn dot linear model import linear regression model is equal to linear regression, and you just call model dot fit X train, Y train, and you can also compute the score. It's a lot cleaner than model stats. So I'll advise you to maybe look into this as well. Okay. Sklearn dot this linear regression. They also have similar case for logistic regression. The only thing is stats model gives you a lot of parameters. That is that F test, Z test, R chi-square values, and so on. This won't give you that probably. They're only good for machine learning tasks, not for statistics. But a good library nonetheless. So let's move to logistic regression. Yeah, by the way, one last thing, if the plot is too big, you can control its width. Yeah, better. So let's go to this part. We have GitHub, repo, week 8, Iris. Load this data set. This is a classification data set. You have three classes in this case. Okay. So take take a minute to think about it, that in this case you have df.species.unique. You have three classes: Setosa, versicolor, and virginica. Now, if I ask you to do logistic regression over this data set, how will you do that? Think about it for 5 minutes and answer me. Any idea how to do it? I mean, why can't we just use logistic regression as is? Pass the training data, pass the test data. What will happen? Anyone? Okay, so let's look at the curve for logistic regression.
Will logistic regression be required in this as such, because we can assign dummy variable regression to this one, right?
Okay, so let's say I assign dummy variables. I have three. So what will I have?
0, 1, 2.
Okay, so I'll have 0, 1, and 2. Okay, so I have three. And what now? I have to use logistic regression. Do you see any problem? So for example, in this curve, can you see this plot where my cursor is?
Yes.
Yeah, so logistic regression says above zero point 0.5 you are class 1, below zero point 0.5 you are class 0. Okay, I have three
Mhm.
classes. So how will I
Uh,
decide who is who?
mhm.
Yeah, so that's the point. Logistic regression only works with two classes. It doesn't work beyond that. So how can we extend logistic regression to more than two variables? Can you think about that? So in such cases, there are actually two options. One is called one versus one. The other is called one versus all. So pay attention to this. Am I audible?
Yes.
Yeah. So in one versus one, what we try to do is, for example, we have three classes, as you said, let's say 0, 1, 2. I'll train a classifier for 0 versus 1. It will tell me, am I class 0 or class 1? Then we'll have 0 versus 2. Then I'll have 1 versus 2, 1 versus 3, and then what's left? We have 0, 1, 0, 2, 1, 2, 1, 3. Then we'll have 0. In fact, I can have 0 versus, I think we have everyone. 1, 1, 2, 4. Yeah, 3 choose 2.
One versus
Correct.
three won't be there, na?
Yeah, there is no 3. Correct. Yeah. So we have three models like this. So for example, let's say 2 versus 0. Okay. So what we do is when we have models like these, I'll train three individual models. Model 1, model 2, model 3. For every prediction, for example, I get some data, I have to make a prediction. I'll pass it through every one. Okay. This will give me some confidence. That is, with 80%, I am confident that I am class 0. With 80%, I am confident I am class 1. With 80%, I am confident I am class this. Among the three, whichever gives me the highest confidence, I'll take that. Okay. That's for one versus one. For one versus all, we say 0 versus not 0. Then we say 1 versus not 1. And we say 2 versus not 2. So this would actually be more important. For example, let's say we had four classes 0, 1, 2, 3. In this case, 4 choose 3, I'll get how many? 4 factorial? No, 4 choose 3 is 4. Yeah. So 0 versus 1, 0 versus 1 versus 2, 0 versus 2, and I'll also have 0 versus 3. And then I'll have 1 versus 2, 1 versus 3. And finally, what am I left with? 0, 1, 0, 2, 0, 3, 1,
Two,
2,
two,
1, 3,
three.
and that's it.
Two, three.
Yeah, correct. 2, 3. 2, 3. But 1 versus all will remain the same. So 0 not 0, 1 not 1, 2 not 2, 3 not 3. In 1 versus 1, you create pairs and then you train a model. In 1 versus all, you pick a model and you assign everyone to not that model. Okay. So for example, 0 and everyone else, 1, 2, 3 falls into not 0. Similarly, 1 and everyone is not 1. Correct? So in this case, you have to train a lot more models. In this case, you train relatively fewer models. And the idea remains the same. When you have to make a prediction, you have to pass it through every model. Whichever one gives you the highest confidence, for example, 90%, 95%, and so on, you take that. Make sense? Very expensive, but I mean, that's the only way to go if you're using logistic regression. Any confusion?
Basically, when we are sampling for training the data, it always
Hmm.
randomizes the confidence level. right? So if I go through each of them one time, it might give me like say 85% confidence in 0 versus 1 compared to let's say 99% confidence in 2 versus 3. But if I run it again, it will give me some different values, right?
No, actually, I'm not deciding on one model. I'll always have four models. When I get one instance, for example, I'll take one row. When one row shows up, for example, this row,
Mhm.
I'll pass this row into this model, get one prediction. This model, one prediction. This model, one
Ah,
prediction. This model, one prediction. Everyone will give me
mhm.
some confidence. Let's say the first one says I am 70% sure that you are class zero. The second one says I am
Mhm.
10% or maybe 40% sure, and so on. Whichever one gives me the highest confidence, I'll take that.
Ah, okay, understood.
That way. Yeah,
Yeah.
all models are trained individually, but at test time, you use them at a time.
Okay.
Yeah. So for stats model, if we look at this, in stats model, they had something called logit, which is for logistic regression. This works with binary cases. Okay. Another one is stats model LN logit. I think it was MN logit. Yeah, so this is for multi-class, but for some reason this doesn't work quite well. I tried to get it to work, but it didn't work. So I'll stick to this part, logic. Maybe you can try this one later. I tried from my side, it didn't seem to work. For example, it expects that thing, what I said. I mean, n cross this thing and so on, so on. It doesn't work for some reason. Sklearn works, this doesn't work. So let's say we want to work with this data set. Upfront, we have to decide which class. For example, we'll use one versus all. Okay. For using one versus all, we'll say um, create a copy. Let's say in this case, I have Satosa, df dot species dot unique. Let's say we'll do for Satosa and not Satosa. So I'll say df Satosa is equal to df dot copy deep is equal to true. I'm creating a copy of the full data frame. Within the copy, I'm saying do one thing. In for its species column, apply a function to it. The function says set me to 1 if I am Iris Satosa, otherwise set me to 0. Mm, so if we print the head now, didn't change. We get these species 1, species 0, and so on. Okay. So in this case, versicolor and virginica both have gone into 0 class. So now everything else is the same. That is, we add a constant term for the coefficient. We call model is equal to, in this case, logit, and then we call model dot fit, and that gives us some parameters, and we can once again use predict. So can you try that from this point on? Can you attempt that? Use this. Let me share the link. I'm not saying anything. Can you hear me?
Yes, sir.
Yes, yes.
Oh, so let me know. Let me know once you're done. Any progress?
Model is throwing errors. So trying.
Stats model has a lot of functionality, but I will still prefer sklearn over it for some reason. Sklearn requires a lot less code, I believe. Okay, so let's start, huh? Before everything, let's create a train rest split, and this time let's do it using scikit-learn. Let's say from scikit from sklearn dot model selection import train test split. Yeah. So we have train test split, and we have to pass it df underscore satosa without the species column. So this becomes our training X data, and the Y data is just species. We have these two. We want to set a random state, let's say 0, and the most important parameter is stratify. Stratify says, let's say I had 70% class 1 and 30% class 0. Split the data so that the training set has the same distribution. So this makes it very, I mean, it makes sense to generalize this way. That is from going from train to test. If you do it randomly, it may so happen that you have a class imbalance in one of the two splits. So you ask it to stratify based on species. So this will return four values. If I just write it here, we have training data, Y, a random state, and a stratification. It will return four things. The first is X underscore train, the training value, X underscore test, Y underscore train, and Y underscore test. It returns four things. Once we have this, we will add a constant just like we did last time. So we had those lines here, these. Yeah, we go to this point, we add here, and we can do one more thing. We can use the NumPy array rather than the Panda series. So we have xtrain, we have xtest. Now comes the model. So model in this case is sm dot logit, and it takes the same two things, I believe. Yeah, the endogenous variable and the exogenous. The endogenous is y train and the exogenous is x train. So we have these, we have these, then we fit the model. We'll say results is equal to model dot fit, and later on we'll make prediction. Let's see if this much runs. Species not found in XCs. Species has S small. Mm, what happened? Oh, we're not df underscore setosa underscore setosa. Yes, seems like it worked. So if we predict something, so let us say Fred underscore train is equal to model dot predict, and we pass x underscore train. What do we get? Not aligned with this. Uh, oh, results. Yeah, I think it worked. Let's do it in a separate cell. So this works. Let's clear the output. We have results dot params. Yeah, so we have the parameters. We can also make predictions. So for example, our red train looks like this. These are probabilities. To convert these probabilities to classes, there's a simple hack. We'll say red underscore train is greater or equal to 0.5. This will convert every value to either true or false. Then we can change those true false values to integers, and a true will be converted to 1, a false will be converted to 0. So if we print it after this, we get the predictions. If we compare them to these, we can compute the accuracy as follows. We'll say y train is the same as Fred train. This part up to this point will give me true false values. I'll take the sum. In the sum, true is counted as 1. So the sum gives me how many are the same. And then I just divide by y underscore train. Print ACC. It has 100% accuracy. So don't be fooled on this part, because actually, if you we did it for Setosa versus not Setosa. If you actually try it out, for example, for versicolor, for some reason, stats model performs very badly. The training accuracy comes out 33%. While as if you train the Sklearn model, it will go up 98%. And I could not, I mean, debug this part, why it happens. So let's try that. Let's say we go for versicolor now. Everything remains the same. We pick up this part. I think this part, yeah. So we have df setosa. Instead of this, we have df versi. Let's keep it df versi. This is this versi dot species. VRSICOLOR, and we have df dot versi dot head. Okay, so these become 0, rest become 1. Then we once again create a train test split, and we have to change setosa everywhere. So becomes versi, versi, versi. This remains the same. This remains the same. The results becomes the same. And in this case, I believe it doesn't actually find the correct answer. So if we take these three cells. So we have the predictions. Yeah, everything is zero. So it actually didn't find anything. But if you do the same thing using scikit-learn, it works. So for example, from sklearn dot linear model import logistic regression, and you say model is equal to logistic regression, and we say model dot fit x train y train model dot score x train y train uh, needs at least, what did I pass? Yeah, y train has everything zero. I think we wrote the wrong spelling here. Versicolor, what was it? VRSICOL, it's the same. So if we do this again and we check the species, df underscore versi dot species, what did I name it? So we have our data frame. I copy the data frame into versi. Oh, I do this, and to check what happened. Yeah, this time we have two values. So we come df.versi, df.versi, df.versi. Species is dropped. Values are the constant x train, y train. We get the model. Oh, in fact, it did it this time. So if we do it again, we also have y train. And if we print the accuracy like last time, yeah, 74 works good. So similarly, you can create another one for the third one was, I believe, Virginica and not Virginica. Then when you get to the test set, you have to pass them through all three. And the one that gives the highest confidence level, you take that as the prediction. So that's a lot of work. In fact, you can, I believe, use scikit-learn's logistic regression, and they allow you to do one versus all and one versus one. Let me see. Sklearn multi-class logistic. Yeah, one versus one classifier and so on. So you can maybe look these things up. See all anywhere. Mhm. Yeah, so maybe so look into this part. Otherwise, when using stats model, you'll have to create as many models as you have labels. So does anyone have any confusion in this? We'll end the session in that case. Is there any confusion in training the logistic regression from stats model? Making predictions, converting the predictions to to integers, calculating accuracy, anything?
No, sir. Like like related to second learn. Like
Uh-huh.
like I have practice on the second learn, but I will make sure the practice about the other one.
Yeah, so look up that thing, one versus all and one versus one. I have used that, but I don't know whether it is part of logistic regression or whether it comes as a separate class. So maybe look into that. That basically allows you to do all of this in one line. You pass it the data set and it will create multiple models itself. So I think we'll stop here. You'll find
Okay.
the code at, yeah,